Let's discover exactly what is a programmable logic controller. They're used in a very wide variety of industrial situations. They're basically a computer that are designed for operating machines, and that they're made so that it's very easy to connect input and output to it. For example, let's just say you wanted to hook up a start-stop switch for a motor, or for, better yet, for a machine of some kind. What if you tried to use your desktop computer to control that machine? Well, how would you hook up the start-stop button? Well, you'd have to make a program and click something on the screen, but what if we want it to be simple and just push buttons? Well, there's not really an easy way to get that into your computer, right? There's not an easy way to just connect a single switch into your computer. PLCs are also designed to be ruggedized. They're designed so that they can survive in higher temperatures and lower temperatures than standard computers are designed to operate in. They're designed to be very reliable. Even some of the Linux operating systems nowadays, seems like you have to reboot them every month or so. Windows, if you don't reboot it every day, most often you run into some kind of problem. Even I just got a smartphone recently, and I held out as long as I could, and I was so embarrassed. I was trying to get it to do something, and it didn't work. It had worked to that point, and I finally called the technical support. I said, well, what's wrong? What should I do? And they said, well, have you tried turning it on and off again? So sure enough, I rebooted my smartphone and it worked fine. So PLCs are not like that. PLCs are designed to be very reliable, to literally get all the bugs worked out so that they just work. You can leave them on often for years without any problems, and they still work just as well as the day they started. Typical Windows operating systems, any operating system nowadays, seems like will slow down as you do more and more with it, or it stays on for a long time. And PLCs are not like that, which is a huge advantage. They're also designed so that the language that you program them in is fairly easy and intuitive to understand. At first, PLCs were used to replace relay logic. Relay logic was just designing a control system where you had a whole panel of relays to do sort of if-then. So for example, let's say you have a process where you need to bring it apart, heat it up, and send it on. This needs to be done thousands of times a day. You don't want a person sitting there doing that. That's very boring. So you might use relays to turn on the motor once you sense that the part's in place, turn off the motor, turn on a heater. When a temperature switch is triggered, then turn on the motor and move the part out, turn off the heater at the same time. That's logic, and you can do all that with relays. You can basically make a program with relays that will control a system like that with input and output. But PLCs were introduced to replace relay logic. Basically, the structure of a PLC is the same as that of a computer, except, as I said, it's been ruggedized. Now, a lot of times what you'll notice is that the PLC, yeah, it has memory, it has a processor, all the things like a computer would have, but there's a couple things missing. For example, you don't have a keyboard and mouse. You don't have a nice big display. Also, typically there's less memory and a much lower processor speed in the PLC versus, a state-of-the-art computer. Now, here's a visual representation of relay control on the left and PLC control on the right. Both of these are inside of control cabinets, and I don't know what the one on the left is designed to do, but let's see, it looks like it has 1, 5, 6, 7, 8, 9. Looks like it has 9 relays in it, and maybe even a blank spot on the lower right, unless that's a fuse box. But anyway, the point is, the way that you change the relay logic program is you got to rewire it, and that's a big pain. I mean, even with this very small number of relays, which could only do very simple control things, this is very difficult to look at, understand what it's doing, and then change it to do what you want. Also, the cost of those relays is probably more than the system you see on the right-hand side. The system on the right-hand side is a little bit different. It still has some relays. If you look down at the bottom, there's 2 motor starters and overload relays in there. So it's still got some relays, but that's just because the PLC can't switch a whole lot of power. But it can do all of the control logic and a whole lot more than the system on the left is doing. Not only that, but the PLC itself probably costs less than all those relays together. So you can either choose to buy, 10-11 relays that can't hardly do anything, are expensive and prone to failure, or you can buy a PLC that has millions of relays essentially in it for doing control and making decisions about when a part needs to be pushed out of the system and so forth. Now, PLCs, as I said, originally just replaced these on-off types of relays, but since they are computers, they're actually much more capable, and so nowadays they do a lot more analog control as well as digital control. So the nice thing about it is that, number one, the relays are cheaper in the PLC because they're internal. They're basically solid state relays in a sense. They're really just, memory and processor. And so they don't break like regular relays do. In fact, in that relay cabinet I showed you with the relay logic, you might notice all those are ice cube relays that are mounted on a base, so a terminal block base. And the reason you do that is just because the relays give out. They're mechanical things that move, and they can only switch states so many times. They have a lifespan. Transistors inside of solid state memory and CPUs and so forth can switch trillions of times in their lifetime without any ill effects. You try doing that with a switch that's opening and closing, it's going to beat itself to death. So the reliability of the PLC is much, much higher. It's less adversely affected by use than the regular relays. Also, it's really easy to change the program in memory. You just reprogram it, and you don't have to worry about making a wiring error and then scratching your head wondering why your relay logic is not working right. So it's much more flexible. You can hook in all the different inputs, put them wherever you want, any input terminal. You can't put more than one input to a terminal, but that's okay. PLCs usually come with a whole lot of input and a whole lot of output terminals, and just wire up the outputs to wherever it's convenient, and then write the program to connect it together however you want with the logic that makes the decision, given all these inputs, what should the outputs be? That's basically what a PLC does. So, like I said, usually a small PLC will cost less. Now, there's a whole wide range of PLC costs. You can buy, I've got a PLC downstairs in my home that controls my heating and cooling system, and I've probably got, well, let's see, it's a Click Koyu, I've probably got $100 in the PLC itself, the brain, the input-output modules. I needed a couple of thermocouple modules. Those actually were more expensive than the brain. They were about $150 a piece. I think I got 2 of those. So far we're up to $400. I've probably got 2 or 3 $50 I/O cards because I needed different voltages. So say 150 plus whatever it was before. I think it was 400 or so. I've got about 550, maybe $500 in that PLC. But the only reason there's so much money in it, which is really not much for PLC, but the reason there's so much in it is just because I kept adding stuff to it. I wanted it to do more. And because of the way I've got it set up, I save a whole lot of money in fuel costs. So it was worth it to pay for this PLC and let it control my HVAC system. If I sometimes sell this house or pass away unexpectedly, I feel sorry for the next person that comes in and tries to figure out what the heck I did to make it work. But anyway, you'd be surprised how quickly the cost of relays piles up. So to get enough relays to control the system the way I have it, it would take a whole lot of relays and would be a lot more cost than the system that I have. Plus, it wouldn't have the ability to read temperature from thermocouples like my system can do. The other nice thing is that the PLCs have communication capability. So if something's going wrong, if I don't like the way that the system's operating and I decide, hey, I want to change the program, I literally sit upstairs at my other computer and I connect to that PLC remotely and I just upload a new program. I write the new program and upload it. So it's really nice because in industry, PLCs can be communicated to remotely, and so you don't have to go out on the factory floor. You can just sit at your office, connect to the PLC, see what its inputs and outputs are doing, update the program if necessary. And it's not just a matter of programming the PLC. Often PLCs need to communicate information like how many items they've produced in a certain amount of time, or when something's ready to move on to another station that's under the control of some other system. Like, let's say you have a robot that loads a milling machine, a CNC milling machine, off of a conveyor. Well, the conveyor is probably controlled by a PLC. The robot is controlling itself, and the robot has to be able to tell the CNC to go once it's put the part in place, but also it needs to be able to tell the PLC, yes, I've picked up the part that we both know is at the end of the conveyor. And the PLC needs to be able to say, hey, there's a part at the end of the conveyor. So this communication on the shop floor between electronic devices is very important and is more difficult to do with relays, whereas with PLCs, it's relatively straightforward. Now, In relay logic, if you think about the switches in the relays, it takes time for them to make contact or break contact. There's a significant amount of time required that to you and me as human beings might seem fast, but on the scale of electronics is extremely, excruciatingly slow. In the case of a programmable logic controller, the changes in the transistor states happen very, very fast, much faster than the change in state of the mechanical switch inside of a standard relay. So PLCs can respond to events much, much faster. When a sensor is triggered, the PLC knows about it immediately. But when a sensor is triggered for relay logic, the relay has to switch state, and that takes time. And so PLCs can have much faster response and can actually respond to things much faster. For example, here we've got a line of bottles going by. So maybe we want to count each bottle as it goes by. Well, if the bottles are flying by too fast, we're going to get more triggers from these bottles than the relay logic could keep track of. The relay simply would not be moving as fast as bottles are going by. And so, PLCs don't suffer from that. PLCs can sense changing sensors much more rapidly than relay logic can. Obviously, it's easier to troubleshoot a PLC. Usually the way you do this, there used to be teach pendants and things, well, not teach pendants, but programming, there's a name for them. Handheld I can't remember the name, it doesn't matter. They're old enough, I've never even used one. Every time I've programmed a PLC, and I've been programming them since about 2004 or so, I've used a laptop and just connected to the PLC either over the network or next to it, or a desktop computer for development, and just uploaded my program or downloaded the program from the PLC, modified it, and did whatever I want. The nice thing about PLCs, though, is that you can look at the program and see it operate. The ladder logic program that the PLC runs is easy to monitor on say a laptop screen, and when things aren't working the way you expect, you can actually go through it and just see why the output you expected to come on or go off did not go on or go off. It'll be right on that rung, and you might have to trace it back a few rungs, but it's much easier to troubleshoot. If you hook up a set of relays and you try to troubleshoot them and they're not working right, you've got hundreds of wires and each one could be wrong, any one of them causing the problem that you're observing. Whereas the layout of a ladder logic program is much easier to understand, much easier to troubleshoot therefore as well.